Okay, people, so this is Fluids Review Solutions. Ready, set, go. Number one, a manometer measures which of the following? Pressure, G. Wonderful. Number two, 19 seconds, one question answered. World record. Number two, a tank. Here we go. This is where it starts to get trickier. Tank is filled to a depth. I'll just tell you right off the. No, I won't just tell you. Sure. No. All right. Tank filled to depth of m meters with water. Atmospheric pressure equal to 0. Sure, fine. Point X is 2 meters from the bottom. Here's 2 meters, and this is X. And then point Y is 4 meters from the bottom. And we want the ratio Px over Py is 3 over 2, and we want to know what m is. All right, now, when they say atmospheric pressure equal to 0, that means we can just deal with gauge pressures only, Or we can say, really, that pressure X is rho G times H. Well, that's rho G times m minus 2. Get me? Rho Y, rho G H Y, or rho G m minus 4. So dig this. Px to Py, which is 3 over 2, is also, well, Px is rho G m minus 2. Py is rho G m minus 4. Rho G, gone. So I work with this. So I'm going to cross multiply. 3 times m minus 4 is 3m minus 12. 2 times m minus 2 is 2m minus 4. Solve. M equals 8. Okay? That would be B. Number 3. A flat piece of sheet metal. How deep is the lake? Is your lake? That's a Bee Gees song. How deep is the lake is the question here. Number 3. So we got this sheet of metal down here, and specific gravity. We all know what that means. Specific gravity is rho of the salt water to rho of water is 1.25. So that means that rho of salt water is 1.25 times 10 to the third. Force of that, well, we know that force is pressure times area, right? So that's going to be, it says it feels a total force due to, a force due to total pressure. That means P atmospheric plus rho GH times A. So we know all these things except for how deep is the lake is H, right? We're looking for H. So that's F over A is P atmospheric plus rho GH. H is F over A minus P atmospheric divided by rho G, where again, rho of salt water. Solve, you'll get C, 8 meters. How deep is another flat piece of stupid sheet metal? Oh, this is the same problem in opposite order. So knock yourself out. It's E. Number 5. Column of water 3.2 meters high on the cross section of this is able to support an unknown liquid. The ratio of the densities. Well, when it says it's able to support them, what we sort of mean is we sort of mean this. I imagine in my little brain a U-tube sort of thing like this. Are these things too low or too high? Yeah, they are. It's supposed to look more like this. And so, like, in one place you have like this fluid, and let's say like, and then over here there's now this fluid. Okay, but the deal is that the weight of each fluid, mg, m water g, is m unknown fluid g. Okay? Is it water? Yeah. That's the deal. The weights have to be the same. Okay? So that means the mass of the water and the mass of the fluid are the same. Or rho water v volume water is rho fluid v fluid. Or rho area times height water is rho fluid area fluid height fluid. Solve, you'll get, we want the ratio of the two densities. Okay? Yeah. Okay? Okay. 6 or 7 or 6. Yeah. Cylinder is released from rest. The initial upward acceleration, that's no doubt about. There's one of these, FB. So this is rho fluid V object G. It's V object because it's all the way underwater. Is, what do I know here? Mass? I do know the mass. Mass object G. Okay. Oh, no, stupid. Minus mass object G equals mass object A. Okay, now V object is height object times the area of the object. It's a cylinder, G minus M object G divided by M object equals A. I believe that's how I would do this one. Yeah, that is how I would do this one. Right, 6? Yeah, I think that's it. I think that'll do it, because we know, right, rho fluid, we're given, yep, height of the object, check, area of the object, check, G, yes, mass of the object, check, mass of the object, check. We get A. Okay? 7. A piece of cork and a piece of lead. Answer D. Prove it. That's not true. Buoyant force and lead is not greater. They both displace the same amount of fluid if they both have the same volume. Therefore, they both feel the same buoyant force. Number 8. That's a good one. I like this one. 8. You got this, right? You got this thing over here like this. Cylinder has this mg, and it feels this buoyant force B, and therefore the acceleration is FB minus mg over m. Agreed? Now, we cut the, what do you call it? The volume of the cylinder is cut in half, so I'll just cut its height in half like that. Now we have mg over 2. We have, oh, look at this, FB, well remember, this is rho VG, right? The volume of the displaced fluid. Well, that's now half what it was before, which makes the buoyant force half of what it was before. So we get, well, half of FB minus half of mg equals half of mass A. So these 2's all go. It's the same darn thing as it was before. Answer C. 9. Cylinder with a height of 3 meters. Cross-sectional area. That's a big cylinder. Equilibrium when 2/3. Okay, 2/3 of this big old cylinder is like this. Is, wait, 2/3 is submerged. Okay, so we got this, mg, FB equals mg. Equilibrium is established. This is rho fluid, V fluid G equals M object G. We want to know the density of the fluid, so let's get rid of the G's. Density of the fluid. Rho fluid equals mass object over V fluid. Well, that's V object submerged, which is 2/3 V object, right? Equilibrium is established when 2/3 of the object is submerged. So that means that rho fluid is 3 mass of the object over 2 V object. That's just algebra. And the volume of the object is, 3 mass of the object over 2. Hang on, do we give the mass? Yeah, we do. Over 2 times the, again, height of the object, area of the object. Answer C. Number 10. Released underwater and sinks to the bottom. Magnitude is, wow, pretty specific. The density is most nearly. Another buoyancy question. We got mg. We got fb. And it sinks to the bottom. We have mg minus fb equals ma. Or m object g minus rho fluid times v fluid times g is m object a. What do we want here? Density of the object. Ooh, density of the object, eh? So that's going to be in here, I believe. Yes. What else do we know here? We don't know much at all. Ah, dig it. This is going to be rho object, V object, G, minus rho fluid, V object, G. It's submerged. V fluid is V object submerged. Happens to be the entire object. Equals rho object V object A. Right? I'm using the fact that density is mass per unit volume. Therefore, any mass is rho times V. Who cares what the volume of that object is? Algebra says rho object G minus A equals rho fluid G. Rho object is rho fluid G over G minus A. Use G as 9.81 probably meters per second. And you get D. 11. Cube. 80%. Mass of the cube. FB. No. MG. FB. FB. MG. Rho fluid. V fluid. G. MG. We want mass of the cube. See it. Mass of the object. Rho fluid. 0.8 V object equals mass of the object. Do it. Mass of the object is D, 4 kilograms. Okay, we got through the barracudas. Now they go pretty quick from here. 12. Flow speed at point Y. Well, this is A1, V1, A2, V2, or AX, VX, AY, VY. The diameter is 3 times smaller. The speed is, well, if the diameter is 3 times smaller, the radius is 3 times smaller. That means that the area is 1/9 the original area. So that means that V2 is 9V1. 36. E. 13. Water flows through a pipe with a non-uniform diameter. At one point, the cross-sectional area is A. Water flows at 2 meters per second. What's the radius of the pipe at the volume rather than 8 meters per second? So I say this: A1, V1, A2, V2. So this is, it's just given us to us as A. What's the radius? So we have A times 2 meters per second is pi r squared times 8 meters per second. Or a over 4 is pi r squared. Answer A. 14. Oh, yes. A. 15. Do I need a whole page for all these? B. 16. Yeah, sure. Now I do. 16. Small hole made a distant section above the bottom of a large water tank. Water, I believe, is at 26 meters. Hole. Spewing, doesn't go up. Spewing water. I'm going to bring a bucket tomorrow. We're going to spew some water around. This is 20 meters per second. The question is, what's this? So this is Bernoulli. P, 1, plus rho GH1 plus 1/2 rho V1 squared. P2 plus rho GH2 plus 1/2 rho V2 squared. Conservation of energy. Well, let's see. We'll call this 1. We'll call this 2. Open to air, open to air. Height 2, 0. V1, 0. Assumption, right? We're assuming that. It's pretty darn close to 0. It's very small, very small. Rho GH1, rho V2 squared. Rho. H1 equals V2 squared over 2G. Oh, we don't want this x, do we? We want this x. So this is 400 over 20, that's 20. We just found h. We found h, but we want x. X equals 6. Answer. Where are you? It's D. If you use this as 19.6, right, you'll get something a little bit different. A little bigger than, right, it'll be 20.4 or something. Okay? Okay. 17. Bernoulli's equation is A. Repeating that. 18. Good one. 5 to 2 to 4. What? E. Flow rate always the same. 19. Yeah, I will tell you it's C. All right, another Bernoulli, just basically just like this, except easier. Bernoulli. 20. D. 21. It's a crazy rectangle over here, but by the time you get over here, it's a, oh boy, it's a circle. Oh wait, I'm gonna try this. Oh, yeah, what's up now? Oh, yeah, not bad. It's like a, never mind. Water, okay, so this is length, no, this is width, and it's moving here with a speed v. We want to know the velocity here. So, A1v, we'll call that 1, is A2v. Here's 2. Well, length, width, V1, which is V, is pi r squared, the V we're looking for. Pi r squared. The answer is A. 22. A. 23. C. 24. A. 20 minutes on the nose. See ya. See ya.